Connecting a copper conductor to rebar in a concrete encased electrode increases the overall conductivity because rebar has a higher conductivity than concrete itself. This allows the electrode to make better contact with the surrounding soil. Rebar provides additional surface area for the electrode to come into contact with the surrounding environment, improving its grounding ability. Concrete is a poor conductor of electricity when dry. By connecting to the rebar, the electrode has a better chance of making contact with moisture in the soil, even in dry conditions. Section 250.52A3 of the National Electrical Code specifically states that concrete encased electrodes consist of the listed options, which includes rebar, metal underground piping, and metal frames of buildings. The use of a 20-foot copper conductor alone is not considered a concrete encased electrode. The NEC does not specify a minimum resistance requirement for concrete encased electrodes, but it is generally accepted that a resistance of 25 ohms or less is desirable. Using a 20-foot copper conductor alone may not provide a sufficiently low resistance to meet this guideline. While 250.52A3 permits the use of a 20-foot copper conductor as a concrete encased electrode, it is not sufficient by itself. The NEC requires that concrete encased electrodes consist of the listed options, which typically include rebar. Connecting the copper conductor to the rebar enhances the conductivity, surface area, and performance of the electrode, ensuring a reliable grounding system. When installing a grounding electrode system, several factors influence its effectiveness. Firstly, the conductivity of the surrounding soil plays a crucial role. Soil with higher moisture content and dissolved salts generally exhibits lower resistance, facilitating better current dissipation. Secondly, the depth and surface area of the electrode are significant. Deeper installations often encounter more stable soil conditions with consistent moisture levels. A larger surface area allows for greater contact with the earth, reducing resistance. Thirdly, the material used for the electrode affects its performance. Copper is a common choice due to its excellent conductivity and resistance to corrosion. However, other materials like galvanized steel are also used depending on soil conditions and cost considerations. When dealing with concrete encased electrodes, the connection to the rebar network is vital. The rebar acts as a conductive grid, increasing the overall contact area with the concrete and surrounding soil. This is particularly beneficial in dry conditions where the concrete's conductivity diminishes. The 20-foot copper conductor mentioned in 250.52A3 provides a supplemental path for current flow, but its effectiveness is enhanced when integrated with the rebar. The NEC emphasizes the importance of a comprehensive grounding system to ensure safety and prevent electrical hazard. The code outlines specific requirements for electrode size, installation depth, and bonding methods to minimize resistance and provide a reliable path for fault currents. Proper grounding is essential for protecting equipment and personnel from electrical shock. To achieve an effective grounding system, consider the following steps. 1. Conduct a soil resistivity test to determine the soil's conductivity. This will help determine the appropriate type and size of grounding electrode needed. 2. Install the grounding electrode according to NEC guidelines, ensuring proper depth and spacing. 3. Bond all metallic components of the electrical system together, including service equipment, enclosures, and metal piping. 4. Use approved connectors and bonding techniques to ensure low resistance connections. 5. Regularly inspect and test the grounding system to verify its integrity and effectiveness. Common grounding electrode types include ground rods, ground plates, and concrete encased electrodes. Ground rods are typically driven vertically into the ground and are suitable for most soil conditions. Ground plates are buried horizontally and are used in areas with shallow bedrock or high water tables. Concrete encased electrodes, also known as UFA grounds, are embedded within concrete foundations and offer excellent grounding performance due to their large surface area and intimate contact with the earth. In addition to grounding electrodes, bonding conductors play a crucial role in creating an effective grounding system. Bonding conductors connect metallic components together, providing a low impedance path for fault currents to return to the source. This helps to quickly trip circuit breakers or fuses, preventing electrical hazards. The size of bonding conductors is determined by the size of the overcurrent protection device in the circuit. The NEC provides tables and guidelines for selecting the appropriate bonding conductor size. Proper bonding techniques are essential for ensuring low resistance connections. This includes using approved connectors, removing paint or corrosion from mating surfaces, and tightening connections to the proper torque. Regular inspections and testing are crucial for maintaining the integrity of the grounding system. Visual inspections can identify damaged or corroded components. Ground resistance testing can verify the effectiveness of the grounding electrode. If high resistance readings are obtained, the grounding system may need to be upgraded or repaired. The NEC also addresses the use of supplementary grounding electrodes. Supplementary electrodes are used to improve the performance of the grounding system in areas with high soil resistivity or where a single electrode is not sufficient. Supplementary electrodes should be bonded to the main grounding electrode to create a common grounding system. Surge protection devices also rely on a properly installed grounding system to divert transient overvoltages to ground, protecting sensitive electronic equipment from damage. The effectiveness of a surge protection device is directly related to the quality of the grounding system. In summary, a well-designed and properly installed grounding system is essential for electrical safety and equipment protection. Understanding the principles of grounding, following NEC guidelines, and performing regular inspections and testing will help ensure a reliable and effective grounding system. The goal is to create a low-impedance path for fault currents to safely return to the source, minimizing the risk of electrical shock and equipment damage. Let's delve deeper into the specific requirements of NEC Section 250.52A3 concerning concrete encased electrodes, often referred to as U for ground. This section outlines the criteria for utilizing concrete encased electrodes as part of a grounding electrode system. It specifies that a concrete encased electrode must be encased by at least 2 inches of concrete directly in contact with the earth. This ensures that the electrode is effectively coupled to the surrounding soil, maximizing its ability to dissipate fault current. The code allows for 2 primary configurations for concrete encased electrodes. One option involves at least 20 feet of bare copper conductor, not smaller than 4 American wire gauge AWG. This conductor must be encased within the concrete foundation or footing. The alternative option involves the use of rebar, which is the steel reinforcing bars commonly used in concrete structures. If rebar is used, it must consist of at least 20 feet of one or more steel reinforcing bars that are at least 1/2 inch in diameter. These bars must be bonded together using approved methods such as welding or clamping to create a continuous conductive path. It's important to note that the NEC does not explicitly mandate connecting the 20-foot copper conductor to the rebar within the concrete encased electrode. However, as previously discussed, doing so significantly enhances the electrode's performance. By bonding the copper conductor to the rebar, you effectively increase the overall conductivity and surface area of the electrode, leading to improved grounding capabilities. The NEC also addresses the use of multiple grounding electrodes. If more than one grounding electrode is installed, they must be bonded together to form a grounding electrode system. This ensures that all electrodes work in unison to provide a low impedance path to ground. The bonding conductor used to connect the electrodes must be sized according to NEC Table 250.66, which is based on the size of the service entrance conductors. In addition to the requirements for concrete encased electrodes, the NEC also covers other types of grounding electrodes such as ground rods and ground plates. Ground rods must be at least 8 feet long and must be driven into the earth to a depth of at least 8 feet. Ground plates must have a surface area of at least 2 square feet and must be buried below the permanent moisture level. The choice of grounding electrode depends on site-specific conditions such as soil resistivity, available space, and local code requirements. It's crucial to consult with a qualified electrical engineer or electrician to determine the most appropriate grounding electrode system for a particular application. Proper installation and maintenance of the grounding system are essential for ensuring its effectiveness. Grounding connections must be made using approved methods and materials to prevent corrosion and maintain low resistance. Regular inspections and testing should be performed to verify the integrity of the grounding system and identify any potential problems. The NEC is updated every 3 years to reflect changes in technology and industry best practices. It's important to stay up to date with the latest edition of the NEC to ensure compliance with current code requirements. Many jurisdictions also have local amendments to the NEC, so it's important to check with the local authority having jurisdiction to determine any additional requirements. Grounding is a critical aspect of electrical safety, and proper grounding practices are essential for protecting people and property from electrical hazards. Understanding the requirements of the NEC and following industry best practices will help ensure a safe and reliable electrical system. The concept of a qualified person is also important to understand. According to the NEC, a qualified person is someone who has the skills and knowledge related to the construction and operation of electrical equipment and installations and has received safety training to recognize and avoid the hazards involved. Only qualified persons should perform electrical work, including the installation and maintenance of grounding systems. It's also important to use appropriate personal protective equipment (PPE) when working on electrical systems. This may include items such as safety glasses, gloves, and insulated tools. Always de-energize electrical equipment before working on it, and use lockout-tagout procedures to prevent accidental re-energization. Following safe work practices and using appropriate PPE can significantly reduce the risk of electrical injuries. In addition to the technical aspects of grounding, it's also important to consider the legal and liability aspects. Electrical contractors and installers can be held liable for damages or injuries resulting from improper grounding practices. It's crucial to have adequate insurance coverage and to follow all applicable codes and standards to minimize liability exposure. Grounding is not a one-size-fits-all solution, and the specific requirements for a particular installation will depend on a variety of factors. Consulting with a qualified electrical engineer or electrician is essential for designing and installing a safe and effective grounding system. Continuous education and training are also important for staying up to date with the latest grounding technologies and best practices. The electrical industry is constantly evolving, and it's important to stay informed about new developments in grounding techniques and equipment. By investing in education and training, electrical professionals can ensure that they are providing the highest level of service and protection to their clients. In conclusion, understanding the nuances of NEC Section 250.52A3 and the broader principles of grounding is essential for ensuring electrical safety and compliance. While the code provides flexibility in the selection of grounding electrodes, it's crucial to consider the specific characteristics of each option and choose the one that best meets the need of the installation. Connecting to rebar and concrete encased electrodes is generally recommended due to its enhanced performance characteristics, but the ultimate decision should be based on a thorough assessment of the site conditions and applicable code requirements.